And we are recording, and we want to check and see. Okay, so it does look test YouTube 3. YouTube test 2. This is actually YouTube test 2. And now Twitch chat is broken. This is bad. Okay. Is anybody else here? Twitch chat. That's bad news. Okay, but you know what I can do? Hi, Rajat. Okay, so I can see. I cannot actually type into Twitch chat from here. But, oh, look at that. I got a notification that I'm streaming. I should turn this to Do Not Disturb. We'll give it a couple of seconds before we see if anybody else pops in, but otherwise it's you and me. How do you like these new backgrounds? I worked on these all weekend. They're very exciting and fun for me. I made this logo online. I made this vaporwave background image. I'm going to switch later. I'm going to switch to the normal study group layout because it's a bit thing. I just did this one because it was a bit ridiculous and fun. And, you know, that's who I am. Minus the fun. I'm just the ridiculous part. So Do Not Disturb goes turn on. So my phone should be silent. No babings. Oh, and I wanted to see, I'm going to test again. Test Twitch. See if it was just a... Okay. So chat is working without a problem now. Is anybody else... Oh, week 1. We actually want week 3. I checked, do I have a link to week 3? Week 3 is already in the list. We don't know. One of the good things about streaming to YouTube is it actually saves all of the sessions. So so if any of the regulars don't show up, they can watch it back later on YouTube, and that's not a problem. So I'm just going to check Twitch to see if anyone else is here. But if you are not speaking, I won't call you out. So I just want to know.
So then we should go with separate the plan. Oh,
that is supposed to be muted. There we go. So I go to my dashboard. And that's not it. Where's my... There's channel. If I go channel, do I see chat? There we go. I'm sorry, Rajat. I should have had all of this done before I began. Okay, so we have some people here. Hello, people, even the ones who are not speaking. We are going to switch to study group mode. And so this week, and for the new people, we'll talk about a bit of an overview, because I see that a few of the names I don't recognize. Everything runs off of the GitHub. A bit of an introduction to myself. I'm a former high school teacher, and I am a programmer with 20 years professional industry experience. And a few months ago, I decided that I wanted to get a new job. And I sort of set my target on FAANG positions at first. So Facebook, Apple, Amazon, Netflix, Google. And over time, I sort of dialed that back. I actually just wanted any new job. But one of the things about interviewing for big tech, the FAANG stuff, is they have the hardest interviews you can do. And so if you study for the hardest interview you can do, you will be ready, in theory, for anything that we will call second or third tier in terms of getting through the process. So yes, I've said I'm a technical architect. I actually just got a new job. That's got to be updated. So this has already paid off for me. If you are following along, there is a way to schedule this for yourself. You can read this yourself. The GitHub repo is Alex Chesser, currently renamed to Tech Interview to Prep course. I will paste that in the chat if you want to follow along. And we've done a couple of weeks already, and so we're up to week 4. Because arrays are zero based. I kind of regret that decision now, but we are in week 4, and so one of the things, one of the people who joined us last week, I think his name was Mississippi Dog, came in asking about where would you consider putting your or putting your effort into studying. And one of the things, actually, Rajat, you might be interested in this as well. Oops, the referral bonus. That's not what I wanted to link to. I'm going to have to change that. But so Triple Byte as a page is a really interesting. Let me move this off screen and I will log in so that you can. Oh, I am logged in. So Triple Byte is an engineering focused hiring platform, and it's got a couple of things that are really interesting to my mind. First of all, it has some coding quizzes, and I believe as you do these quizzes, they will present you with more. And if you look at this, okay, we can't actually go through it right now because I don't want to burn my account in doing this live with you. But the questions are actually really hard. And what's really nice about how hard those questions are is, first of all, it winds up being a really nice differentiator of prospective engineering skill level. Meaning if you are an early dev, it will, and I guess I'll skip across to my profile. I did one of these assessments, and as a back-end engineer, one would not be surprised to learn that I did okay. I was kind of hoping for a 5 on my, entry level 4. Damn you. Okay, but here in my back end down here, I got actual level 3. So, what it does is based on the quiz it gives you this, and if you score in the level 5, so I can actually, there's a way you can actually zoom in on here, detailed feedback. So it gives you this, it tells you the quiz that you did, it tells you where the scores, how does the balance of the scores happen, shows you that level 5s are here, level 4s are there, and you can click on any of these. So for back end, it says that I'm very good. And anyways, so Triple Byte is a really nice platform, I think, for getting yourself in front of, if you look at the jobs for the companies that list with them. It's a really nice platform for, I wonder if they can filter for companies. Oh, never mind. Not a big deal right now, but we had a discussion at the beginning of, or at the end of class last time, and I was trying to remember the name. You don't actually have to follow my affiliate link, and it clearly looks like it isn't the correct link anyways. But I thought this one was really good because if you score high enough on those quizzes, in theory you get to skip 2 rounds of interview selection. And that's the real killer application part. Let me go back. So if you score a level 5 in some of these things, you can go straight to the in-person interview. So you go straight they can arrange positions where you go straight to the final interview for the tech job that you're trying to get. And so this was one of the great platforms that I saw. It's not quite HackerRank. It's not quite LeetCode. These assessments are not algorithm solving questions, and so you still need LeetCode. You still need HackerRank, but this has the potential to get you straight in front of the companies that you're interested in. So, if a few of the other teammates had shown up, I would have told you. Anyways, I'll skip that one. That's not an important story. Now, Rajat provided us with an interesting package of content. So, if you are interested in boning up on your algorithms and your data structures and everything, we have this stuff, and this is really nice. It's a really short summary of each of the major questions that you're going to run into. And so I thought this was actually a really nice refresher course for dealing with your studying, in getting ready for everything. I imagine if you scheduled a couple of hours a week, you could, and there were exercises and solutions as well. We look at this. So here's an example, an exercise in recursion, answers to I'm not going to read the answers, but I will assume that they are robust. Oh, wow. Okay, I hadn't actually seen this, but that's really cool. So it gives you the question of what you're trying to solve, and you get to solve it in here, and then you look at so this is a really nice, a really nice way to go through. I think if you scheduled, a couple of hours a week, maybe you do 2 nights a week, schedule an hour, you go through this stuff. Oh, look, and he's on GitHub too. Brian, you deserve a star. There you go. Good. That was good work. And there's a present. Anyways, so this was a really good thing, which Rajat sending me that reminded me that we have 2 other really valuable resources that have been around for a long time. Your first year Harvard course in computer programming. So this is CS50. It's a 101 course, but the production value of CS50 is so high. These are so enjoyable to watch. This is a really great way to give yourself either a computer science refresher, or if you're a boot camp grad or a self-taught developer, it can give you those foundational computer science underpinnings that, as a self-taught developer or as a boot camp developer, boot camps get a little more structure in that, but you may be missing some of these key concepts that can come out of that. And let me open it again. If you look at this is, so each week the lecture is hit play. So it's about 3 hours a week. 3 hours a week when it comes out. And so you are looking at 30 hours of class time. That's a lot of work. But again, if you consider the salaries or the compensation and the prestige and the level and excitement of the challenges that you would run into at getting these more complicated jobs, 30 hours of practice for this, or 30 hours of training, is just It's ridiculous. So what's that? That's 1 week of full-time work to double or triple your salary. Let's keep this in perspective. It is a lot of work, but we're here for professional development. And so, and then I also wanted to link to the CS50 YouTube channel, where it is not as structured as this, but if you look, they've got so many really interesting things in here, and they've got solutions to their problems, but they've got these small tracks as well. And so if you already have a robust background and knowledge of programming in general, but you want to have an overview of first year university style overview of Android, for example, or web programming. Rajat, this one might be of interest to you. You can go through. Let's actually look at this, because
in the web programming track, we're going to move from the world of writing command line programs that ran in your terminal to writing programs that now run on the internet. So we'll start by talking a little bit about what the internet is and how it is that computers are able to send messages to one another over the internet. And then we'll take a look at some of the languages involved with designing web applications on the internet, beginning with HTML, a language that you can use to design web pages that web browsers can understand.
Okay, well, you can go back and watch this on your own. But as you can see, the production quality of this stuff is incredible, and the overview is really high quality. So a few years ago, the last time I went through this, a few years ago, they had like a little section on Git, for example, and they had a little section on video game programming, and it was about 7 or 8 episodes of video game programming specifically. Really, really great resource. Highly recommended. You can hop over to YouTube. You can find the link right here. This was supposed to be a link to a document that I found on it on Twitter. David Fowler tweeted it. And let me see. So under Documents, Competitive Programmer's Handbook. What's this? That's in my personal local repo. So the David Fowler, if you don't know who he is a solutions architect, I think, or he's a principal engineer on the .NET Core team, and he is instrumental in creating .NET Core, ASP.NET. Right now, he created the sockets layer for that is very popular and common in .NET called Signal R, and he recommended this book for its he said that this one had a really robust heuristic method of determining the time complexity of a function without getting too mathy, without making it really, and so input output. I don't, but I actually, complexity classes, that might be where it is. So I would recommend looking at this complexity class list to give you a heuristic on how to quickly get an idea of what sort of scaling your algorithm deals with. Those are some of the things that I feel like were left over from last week. Again, I am moving quickly, but these are sort of high level things that we wanted to talk about. Broader, I should fix that, shouldn't I? Let me edit some of this. I've got to fix that later. Fix this link. That's embarrassing too, but we'll see if that works. Does that work? You don't have to use the affiliate link. I'm not at all worried about this. How do you do? Copy. Invite your friends via shareable link. Maybe that's what I need. Try this one. There we go. Let me save that one. This I have to fix later. I have to look up how to do your... And this, I'm trying to fix a broader understanding. So, here we go. Let's get on to the learning objectives of the week. So, the first thing we are trying to do this week, we would like to have a broader understanding of the data structures that we started on last week. And so this is a continuation of last week's learning, where we talked about hash maps. What else? We spent a lot of time on Big O last week. We talked about hash maps. And did we cover linked lists? I don't know. But I know that I wanted to look at some of the things that were harder, that I was less aware of. This is actually, I'd like us to have a plan for mapping each of these major data structures to an existing system within our chosen language. For the new viewers, one of the things we discussed in week 0 was choosing the language that you want to go into your tech interview in. And so for some of us, Rajat was saying he wants to work in JavaScript. For myself, I want to work in C#. For another fellow who came around, Mississippi Dog, he wanted to work in Java. Or was it Python? I can't remember that, but if he's here, he'll tell us. Either way, it's not important what language you choose. You should choose the language that you are most comfortable with. However, I can actually tell a little bit of a story. I have that during the discussion questions, but I think it looks like I have 5 viewers online with us now, and so that's pretty much as high a view count as I expect to show up, so I'll tell the story now. I did another coding interview just recently, and this time I did it for DoorDash. I signed an NDA, so I'm not going to tell you the exact question. It's in poor taste to do that, I believe, but you can. But I can say that the question was really great on the surface because there were so many different ways to solve the problem. And one of the things that you want to go into these coding interviews with is the knowledge and understanding at all times that you're trying to write the optimal solution coming out of that. And sometimes it's not really realistic to write the optimal solution in the time that you have, and so you want to just be able to talk to it. But in the case where I was, we needed to do 2 things. We had to loop through a data set and run a calculation on it. We needed to store that calculation. And then at the end, we needed to select a certain number of elements out of that collection. And so I went in and I wrote the first thing where I loop through once and I build the list. And I used a list, not a hash map or anything. And then at the end, I ran a sort on the list to get the highest values from the list. Okay? Now, what's the problem with running a sort after I've just built the list? Well, I've taken something that was a big O of n, right? So I visit each element in the array once, and now we have a linear time row, big O of n. And now I add a sort after I've gone through every element. And so what I have to add to that, because we know from last week that the cost of a sort is n log n, which means I went from having something that scales with n to something that scales at worse than n. And there is a solution that works very well in a situation where you want to have a sorted data set. And those are trees, specifically red-black trees, or a sorted linked list. So you can get a sorted list, and so my problem. And so I went in and I used a C# list, right, from system_collections.generic, and I sorted the list after running through anything. But there is a type that, had I known of it, had I been aware of it, had I had experience using it before, and had I used the sorted list right off the bat, I wouldn't have had to sort at the end, because as I was building my list, knowing that I had to have it sorted at the end, I would have just been able to pull the top 3 answers, or the top 6 answers, or whatever. I could pull the top answers from this sorted list because I built it right from the start in a sorted fashion. My error that we're talking about right now is not that I didn't do it's that I didn't, in the pressure situation of a technology interview. If I was in a normal situation and this was a critical issue, I would have looked up sorted list and I would be fine. But this is the thing. In that half-hour interview, or in that 45-minute interview, you do not have time to Google around for the best answer and make a couple of bum mistakes, you make a couple of bad choices. So with that said, you don't have any other choice but to use what you know. Had I taken the time in preparation to map each major data structure into something that I knew how to use, I would have felt better coming out of that interview. And so that's a tip that I think each of you should be ready for going forward long term if you are planning to do a tech interview. We're going to have another round later in the lesson about the behavioral side of tech interviews. One of the earliest pieces of advice I received was pay attention to the behavioral, because we spend so much time talking about algos and data structures, and we spend so little time talking about being the right fit. I suspect to some extent that they are. Well, they want high marks in both sections. So, you've got to pay attention to this. Also, wonderful and exciting news. I have reached out to somebody. Amy Miller is a tech recruiter who has worked for Google, Microsoft, and Amazon. She has at least 10 years experience in recruiting for big tech. I can't remember if it's up to 20 years right now. Let's see. But she has this website called So she has 20 years of experience in recruiting for big tech. She has a massive and robust collection of content around. Let's see if I can load her YouTube. She has a really robust. If you go to her YouTube channel, youtube.com, Amy Miller, here she is. A huge collection of videos with the types of questions that somebody who is looking for a job would want answers to. Okay, so there's a question about what do you do when you get your offer? Do I have to negotiate? How do you deal with getting rejected? I've been rejected a lot lately, so I actually watched this one. If you go through this, you will find, and they are pretty bite-sized, 15-minute things. They are answers to specific questions that you might have around recruiting. She seems really nice. She was really approachable. She is going to come on the show next week for 7 o'clock. So I've put together a bit of a plan of a number of things that I want to talk to her about. But if you have questions that you feel like you would like to ask to a recruiter on the inside at a or with connections to the big tech scene, she'll give you some of those answers. And so, yeah, thanks. Oh, that's good. It was, I hope that that's really useful. So I've already told you the experience I had on that other interview. Make sure you know what each data structure is in the language that you're working in. I mean, in JavaScript, it's either an object or an array. I don't know that they have. Well, let's Google it. Let's Google. Does JavaScript have a sorted array? No, they have an array.sort method. They don't. Sorted array collections for JavaScript. I don't think that's that doesn't look, that's collections.js, so that they probably don't have a native structure for that. But anyways, those are some things that I think are interesting. Now, for the rest of the session, yeah, we have dot sort, but the native data type is one that you don't have to call sort on, because as you insert new elements into the sorted list, they get inserted in place at the right position. And so that's so much better than calling sort on something, because you're just building it in a sorted fashion. And so that would have been a far better choice from my perspective. And if I ever see a similar question, I will know from the start. I've got some sort of timings now. I thought that would be helpful. So this is roughly 40 minutes if you watch in 1.0 time. We're going to watch at 1.5. And then preparing for soft skills, we're not going to watch the 20-minute one, but we are going to watch the 5-minute one, and probably watch this one as well. And so we're looking at about an hour of data stuff, and then another 10-15 minutes. So we'll be wrapping up by 8:30 or so. So how are we feeling? TypeScript might. That's a good question. Probably, I would imagine it does, because we just saw that collections.js. So TypeScript, let's Google that. I'm going to Google off screen instead. TypeScript sorted array. Array prototype. Sort arrays using TypeScript. Here we go. So if you go on to GitHub, I'm not sure if this is even, I can't tell, is this TypeScript? Node.js. Source. Oh yeah, so sorted array.typescript. So you can find these things as plugins on the internet, but as we said, it doesn't have a native value for that, which means if you're going into a coding interview looking to find a sorted array, you're not going to have it. Anyways, so there we go. So is there anything based on what we've talked about so far that we want to discuss before we move on to watching the rest of the session, watching some of these sessions? We'll have little chats in between as well, I think. There we go. Resolute, nothing. Gave you enough time. It's a reasonable. Okay, let's get started on stacks and queues. This one is.
Hi, I'm Gail Locke McDowell, author of Cracking Coding Interview. Today I'm going to talk about stacks and queues.
How's the volume,
have a lot of things in common. They are both linear data structures in that you have one element and then another element and then another element. They are both flexible with their sizes, so you don't have to allocate initially them to have a size of like 50. You can just add elements as you go and then also shrink.
Can you hear it okay? Yes. Oh, thanks, Pebs.
It down. The main difference comes in how elements are removed from the stack or from the queue. A stack is what would be called a LIFO data structure. Last in, first out. It's much like an actual stack of plates. The last plate you put on top of that stack, that's going to be the first one you remove. It's LIFO, last in, first out. A queue, though, is FIFO, first in, first out. So think about a queue or a line of people waiting to get into a movie theater. When the movie theater doors open, they don't first serve the person who just hopped into line 5 seconds ago. They serve the person who got in line the very, very beginning, an hour or two ago. And then the next person, the next person. The very first person in is the very first person removed. That's what FIFO means, first in, first out. Now let's look at the code for these data structures. Here's the framework for what our queue class needs. We need this inner class, which is a node, and it just keeps a pointer or a variable that represents the data, and then also each node needs a pointer to the next node. And we gave ourselves a little constructor here. Now when we implement a queue, or when we use a queue, we're going to add things here to the tail and remove from the head. Because we want to add from one side and remove from the other. Okay, and then we need these methods. So let's walk through and actually start implementing these methods. So isEmpty is very simple. Just return if head is null. If head is null, then the queue is empty, otherwise it's not. Okay, and then peek. Well, what peek is going to do is just return head.data. Now this will throw an exception when head is null. If you want, you can go explicitly check for that exception. Okay, so add and remove are the sort of interesting ones. So with add, what we want to do here is add to the tail. So first thing we need to do is actually go and create this node. Then, if tail is not null, but tail's next pointer, point over to this node, and then update the tail. Then what we want to do is we want to make sure that there could be a case where the queue is completely empty, in which case head is null. And so if head is null, then this value head should also be this node. Okay, so that's all add has to do. Okay, now for remove, we want to remove from the head of the linked list. So first thing we need to do is actually get this head data. Then what we want to do is essentially remove that head. So set head equals to head.next, and that basically removes it from the queue. And then we need to say, okay, if head is now null, make sure you set tail to null too, and then go and return that data. So that's the basics of how we implement a queue. Follows pretty logically from the actual design and the algorithms behind it. Now let's look at the stack implementation. Much like with a queue, we have this inner class that is a node class, has a pointer to the next node. Here though, we're gonna...
Let me stop there. one of the things that can come up, I'm told pretty commonly in these questions, is they will say something like implement a stack without using a stack, or implement a queue without using a queue. And so that's one of the things that can come up around this kind of thing. And one of the nice reasons to have this knowledge, so that when they say implement a stack, you know what they're talking about. And you'll also see these questions come up on HackerRank, or they come up on LeetCode. So anyways,
I want to add and remove from the top. So we just need a top. We don't need a head and a tail anymore. And then these are the methods we're going to want to implement. The implementation for isEmpty is pretty straightforward. Just if top is null, return true, essentially. And then for peek, I'm going to ignore null pointer checks just to keep my code really, really simplistic for you all. All peek needs to do is return top.data. Okay, so push is the first interesting method. So first, we need to actually create this new node. So new node, data. Then this new node is going to become the top. So node.next is going to point over to the old top. And then the top points over to node. So that's all push needs to do. Now for pop. Well, so pop is we're going to want to return the old heads data. So first we need to actually just get that data. So top.data. Then top just should be moved and pointed over to the new top, or the next element down. And then we just need to return that data. Pretty straightforward. Now again, I ignored null pointer checks, but if you really want to be complete, you'd probably want to do some sort of check that says, hey, if top is null, throw an exception, if something like that. That's the basics of how stacks and queues are implemented. They're not too tricky to implement, just a little bit of null pointers and making sure to update those things correctly. So now that you've seen both stacks and queues and the implementation of them, why don't you try these out on a new stack or queue problem? Good luck.
Right. Okay. So there's number one. I shouldn't have closed the other one. Yeah, and so that's the kind of thing you would also see in university questions. GitHub Tech Interview Prep course. I somehow closed my week 3. Now we're going to move on to Heaps. Heaps and heaps of fun.
Hi, I'm Gail Locke-McDowell, author of Cracking Coding Interview. Today we're going to talk about a topic that a lot of candidates forget about, heaps. Heaps come in one of two forms, a min heap or a max heap. We'll just focus on min heaps today, because a max heap is essentially the reverse. In a min heap, the elements are all smaller than their children. So the root node will be the very smallest element. And then looking down the tree, down the heap, the elements get bigger and bigger and bigger. So that's the basics of what a heap is. But how do we actually create and maintain such a data structure? So let's start with just insertion. So we insert an element, it always goes in the...
Well, wait a second. That, if I had used a max heap in my code interview question that I was talking about at DoorDash, that would have worked as well. I'm going to Google that on the side, because this is a learning for me.
Next empty spot, looking top to bottom, left to right. So we go, first we insert an element here, and then here, and then here, and then here, and so on through the tree, through the heap. So that's how insertion works. But then, of course, what happens if that's not really where the element should go? Well, what we can do is we can insert the element there, and then bubble it up until we get to the right spot. So we take the inserted element, we compare it with its parent. If it's out of order, swap them, and then keep going up the tree in this process. Now, what about removing the minimum element? So we know the minimum element will always be at the root node. And so that's easy to find, but then if we want to remove it, we might have an empty spot. So what we do here is we remove the min element there, so we take out the root, and then we swap that value at the root with the last element added. And then, of course, that element might not be at the right spot. So we take the root element and bubble it down to the next spot. So we compare the root with its children, its left child and its right child, and then swap it with the smaller of the two. And then we keep going down the tree until the heap property is restored. So that's how a tree operates. Let's think about how a heap operates. Let's talk about implementation now. So implementation is kind of interesting. You might have assumed that we'd implement it as a simple class node with a left node and a right node, and certainly we could do it that way. There's an even better way of implementing it. Note that when we add elements to the heap, they're always getting added in a very particular spot. There aren't going to be any gaps in the heap. So we have the 0th element here, and then the 1st, 2nd, 3rd, 4th, etc. And so that means that we can actually use an array instead to store these values, and that makes it very compact. And a simple equation can map from an index to its left child, its right child, or to its parent. And so we can still get to the left and right child, but we don't need to have this overhead of a node class. So now that we've covered the basics of what a heap is, let's turn to the actual code for this. We'll implement a min heap with a simple class that wraps this items array. This is going to be an array of a fixed length, but if it gets too big, we'll increase the capacity. Now I'm going to get a little bit of a head start and cheat a little bit by just adding in a whole bunch of simple helper methods. So these are just simple methods that get the left and right child or the parent index, actually check if they exist, or actually get the values themselves. So I'm just getting a little bit of a head start here. And I'll get another little bit of a head start by adding in 2 extra methods here. One is a swap method that swaps the values of 2 indices, and another one is an ensure extra capacity method. Now what this does is it checks if the array is full, and if so, it creates a new array of double that size, and it copies all the elements over. And this, by the way, is the basics of how an array list operates. Now let's turn to the real code. The first method I'll implement is a peek method. And this, first it checks if the array is empty. If so, returns an exception because there's nothing at the front. Otherwise, it just returns the first element in the array, which will always be the minimum element and essentially the root of the heap. This method we'll do is a pull method. Now what this does is actually extract the minimum element and actually removes it from the array. So first we'll check if the array is empty. If so, throw an exception. Otherwise, I need to actually get the value. So item is item to 0. Then I need to take the very last element in the array and move it into the very first element. Then I need to shrink my array, or shrink essentially the size of it. And then I need to go and actually re-heapify. So I removed the root element, so I need to heapify down. And I'll go fill this method in shortly. So in this case, if we remove the 10, the minimum element, it's going to get deleted. Then the 17 is going to get moved up to where the 10 is. So see in the array, that's like this. So the 17 gets put in here. And then we go and adjust the heap to shift elements down as needed. My next method is going to actually add an element in here. So first thing I want to do is I want to make sure there is capacity. So I'll call my ensure extra capacity method. Then I'm going to add my element into the very last spot. So items of size equals this new item. Then increase my size. And then I need to actually heapify up. So I need to fix a heap looking upwards, swapping each element with its parent as necessary. So in this case, if we wanted to add an element, say 8, we'd add it at the very last element, and then we'd go and adjust our heap, moving things up as necessary. Now for the real fun, I need to actually implement these heapify methods. So heapify up.
Okay. I just needed I need a second to process what we've just heard. I think this heapified down. So she's saying that she hasn't written these yet, but she says to insert an item, you either remove you either reduce the size and put it into a different place, or you increase the size and you put the item at the size. Okay, so that seems okay.
Is going to start with the very last element added, which is at size -1. And then it's going to walk up as long as there's a parent item, and as long as essentially I'm out of order. So as long as my parent item is bigger than me, then hey, things are out of order. So swap my parent index, swap my value with my parent, and then walk upwards. So let's walk through this on the 8 that was inserted. So what we do here is we'll compare 8 to this 15. It's out of order, so we'll need to swap those values. So 15 goes down here, and 8 goes up here. Or on the array, it'll look like this. Then we compare this 8 to the 10, and then that's still out of order. And so we'll go and move the 10 down and swap the 8 up there. And now we've returned to the heap properties. We have 8 at the top, 10 and 20 below it, then 17 and 15 below that. Heapify down is a little bit more complicated, but it's still quite manageable. First, we're going to start off with our root element, which is at index 0.
What's the time complexity of doing this? Is this actually faster to do this? Well, yes, I guess it is, because in theory, actually, I don't know. I can't tell. I'll have to think about that and try and figure it out. Or somebody
now,
else
to check if there's a left child,
who can
because if there's no
figure it
left
out
child, then there's certainly no right child.
could tell me.
I'm going to set the smaller child index equal to the smaller of the left and the right child. So I'm going to take a guess with set it equal to the left child. And then I'm going to say, hey, if there's a right child, and my right child is even smaller than my left child, smaller child index should equal my right child. Now what I'm going to say, remember I'm looking downwards on the heap. So now what I'm going to say is, hey, if items of index, if I'm smaller than the smaller of my 2 children, then everything's good. And everything's back in order here, and I can just exit. If that's not the case, then our heap is still out of order. And then I need to swap my value with my smaller child. And then move down to my smaller child.
You know what? I can Google it.
All right. So that's the basics of how heapify down works. Let's walk through this on an example. I'll make this example slightly larger. So if we do an extract min, such that 10 gets removed. Then we remove 10, we replace it with 25. I'll do it on the array too, so you can see what's going on there. Then we compare 25, the root, and replace it with the smaller of its left and right child. So we swap the 25 and the 15. So 25 comes down here, 15 comes up there, and we can do it down here too. So 15 goes here, 25 goes here. Then we compare 25 to 17. It's still out of order since 25 is bigger than 17. So we do 17 comes up here, we swap those, and 25 goes down here. So now we have a heap again that looks like 15, 17, 20, and 25. And as you can see, our min heap property has been restored. So now that you understand what a heap is and how it works, why don't you try out using a heap on a new problem? Good luck.
Okay, so I looked this up, and actually, so it says so it actually says each call to heapify, so n log n. So quick look over the above algorithm suggests that the running time is n log n, since each call to heapify costs log n. So log n, it costs log n because you're starting in a sorted array, and each step of the array you only, like, if I skip back, we can actually look at right here. Let's look at her. She has her largest. This is the biggest one we have. So if you're here, every step you go up the chain, you are eliminating half of the other values. And so that is a log of n rather than an n. And I wasn't trying to be a gotcha. I'm legitimately asking this in real time along with the rest of you. And so build heap, suggests the running time of log n and n log n. So there was another one here. There are others. The basic idea behind why the time is linear due to the fact that the time complexity of heapify depends on where within the heap it takes constant time when the node is a leaf node, which makes up at least half the nodes, and it takes log n when it's the root node. And so somebody else did the math because they read that and understood. They read this and understood what was going on. So, again, this is the reason that we do this studying now. So when we are in a code interview situation, like, I don't need to know what that function is, but I should know that if I'm using a heap, or if I'm using a sorted by default data structure that has that sort of left-right pattern, that I'm looking at linear time. And if I was going back to my system earlier, where I was talking about that interview, where I had this thing where I had n log n, if I used a sorted data structure from default, that would have been n, it would be O of n for going through each element in the array once, and then I would have had to say plus O of n for putting it into a sorted array, which in terms of scaling means that reduces down to O of n. So I could have done slightly better in terms of that. So you'll only do max n tries, but most likely a lot less than n. Yeah, that's right. And so your worst case was, and that seems to be exactly right. And there we go. I'd love to hear, has anybody else been going on interviews yet? I'd really love to hear what some of the other experiences are that have been out there, because hearing about the types of questions we get and sharing that information with the rest of the team, well, it just seems good. Seems cool. But while I know that we have a 20 to 30 second delay, so while we wait for answers, I will start us off on trees.
Hi, I'm Gail Locke-McDowell, author
Gail.
of Cracking Coding Interview. In this video, I'm going to
seems so
cover
nice.
trees. A tree is best thought of in this sort of picture. You have a root node at the very top, and it has child nodes. And each of those child nodes, they have child nodes themselves, and so on and so on. Very often when we're talking about trees, we talk about binary trees. A binary tree means that each node has no more than 2 child nodes. That is, that each node has a left node and a right node. Of course, one or both of those could also be null. Very often when we're talking about binary trees, we actually want to talk about binary search trees. A binary search tree is a binary tree which fulfills a specific ordering property. So on any subtree, the left nodes are less than the root node, which is less than all of the right nodes. This ordering property makes finding a node very, very fast because we have a pretty good idea of where it would be. So suppose we're looking for 17 in this tree. We can say, okay, is 17 bigger or smaller than the root node? Well, it's bigger than the root node, so let's go to the right. Now, is it bigger or smaller than that next node there? Well, it's smaller than that node, so it must be on the left of it. And so very, very quickly, we can start to zoom in on where that node will be. Because at each operation, we've chopped off, hopefully, about half of the nodes. And we do that over and over again, and very, very quickly we find the node we're looking for. So it makes finds very, very fast. But how do those elements get in there in the first place? Well, let's talk about how inserts work. Inserts work much like finding an element works. We start with some element we want to insert, like, say, 19. And we say, is it bigger or smaller than the root? Well, it's bigger, so let's go to the right. Now, is it bigger or smaller than that next node? It's smaller, so let's go to the left. And we do this over and over again until we get to an empty spot, or null node. And then we say, okay, that's where we should insert our new element. Now, the one problem here is that if we get elements in a particular order, we could get really imbalanced. Suppose we have a new binary search tree, and we just follow the properties of insertion. So we insert 1, and then 2 to its right, and then 3 to its right, and 4 to its right. We're going to get this data structure that looks less like a tree and more like a long list. And then inserts and finds will no longer be so fast. There are some algorithms that can ensure that our tree stays balanced. That is, that roughly the same number of nodes will be on the left side of the subtree and on the right. These algorithms get pretty complicated, so we're not going to go into the details here. But it's worth knowing that they're built into a lot of programming languages. And in a lot of cases, in interview questions, you'll just assume that you have a balanced tree. The last operation to talk about is traversing, or walking through a tree. So there's 3 common ways we walk through a tree. We can do an in-order traversal, a pre-order traversal.
Here. While this is running, I'm actually going to open a new tab and search in another window to see if JavaScript has a binary tree.
Or post-order traversal.
Just to
A
see.
pre-order traversal means that you visit the root first, and then you visit its left nodes and its right nodes. In an in-order traversal, you visit the left nodes first, then the current node, and then you go to the right nodes. In a post-order traversal, the root node comes up last, so you visit the left nodes, then the right nodes, then the current root node. Typically in binary search trees, we want to do in-order traversals because that actually allows the nodes to be printed in order. So for example, on this tree here, which is a 1, a 2, and a 3, the nodes in an in-order traversal will actually be printed out in the order 1, then 2, then 3. So typically we'll see in-order traversals. Now that we've covered the basic operations, let's take a look at the code for a binary search tree. To implement a binary search tree, we'll need a class node that has pointers to the left node and the right node, and then some sort of data, presumably. And I'm going to give ourselves a constructor just to make our lives a little bit easier. Okay, so the first method I'm going to add is an insert method. And this is going to take in, I'm going to call it value here. This is going to take in a node, or to take in a node value, and look to the left and the right to see where we want to insert it. So first, if value is less than or equal to the actual data of our node, then we should insert it on the left side. If there is no left node yet, then this becomes my new node. Otherwise, then I ask my left to insert it, and I push that down the recursion stack. And then otherwise, if value is bigger than data, than myself, then it should be inserted on the right side. And so if there is no right node, put this as my right node. Otherwise, ask my right to insert it. Okay, so that's the basics of insert. Okay, so let's walk through this code on an example. So we have the simple tree, and we want to insert the value 8. So we call 10.insert of 8, and 8 is smaller than 10. So we go to the left and call left.insert of 8, so 5.insert of 8. 8 is bigger than 5, so we go, and we don't have a right child, and so we set 5's right child equal to 8. The next method I'll do is find. So find is going to operate recursively, just like insert. In fact, it'll be somewhat similar in a lot of ways. And it's going to want to return a Boolean. And actually, I'm going to call this contains because we're not really finding the node so much as checking if the tree contains it. Okay, so first of all, if I'm there, return true. Otherwise, if value is smaller than data, then it should be on the left side. If there is no left node, then I know the answer is false. Otherwise, if there is a left node, go ask my left node what the answer is. now I do the same thing on the right. If, well, I can do student else. If right is null, if there is no right node, then the answer is false. Otherwise, go ask my right child and return its answer. All right, so that's the recursive implementation of contains. So let's walk through this function, imagining we're trying to find the value 8 that we had just inserted. So we call 10.contains of 8. 8 is smaller than 10, so go to the left. And then we do 5.contains of 8. 5 is smaller than 8, and so we go to the right. And then, of course, we see that 8 in fact equals 8, and so we return true all the way up the stack. The final method that I'll implement is a in order of traversal. Specifically, I'm going to print all of the nodes in the tree. So I just call this print in order, and this is actually very simple. First, if I have a left child, then I do my in order printing first of my left child. Then I print my own data. And then, same thing on the right. If right is not null, then I do right.print in order. So remember that in order traversals do the left child, myself, and then my right child. So that's exactly what the code here does. So that's how we do an in order printing. Let's walk through what this code does. So we're going to first call 10.print in order. 10 is going to say left.print in order first. That's the very first thing that's going to happen. Then we're going to print the root, and then it's going to say right.print in order. So we're going to recurse down, and 5, so we can get 5.print in order. 5 is going to say, okay, print, got nothing on the left to print, so print me next, and then call right.print in order, where 8 will get printed. And then we're going to go back up to 10, and 10 is going to get printed. And then we're going to go down to the right in that third step and print 15. So that's how an in-order traversal works. If we want to do a pre or post-order traversal, we do a very, very similar thing, just in a slightly different order. A pre-order traversal means that the root gets printed first. So we print the root, then print the left subtree, then print the right.
So I should stop here for a second to highlight that. Actually, did I paste it in, or give me 2 seconds. I'm going to pull something else up, and I will put this into the week's lesson plan because the value of it was pretty good. I stored this in my. Oh, I'm sorry. I'm gonna keep playing. One of the things, actually, it's up here. One of the things they call out is breadth first search and depth first search, and that I guess that's in graphs, and maybe I'm in the wrong place. Never mind.
In a post-order traversal,
I'm sorry.
the root gets printed last. So we print the left, then print the right, and then we print the root node. So it's a pretty natural translation of the algorithmic concepts. A lot of times in interviews, people get kind of intimidated by the idea of implementing a binary search tree. They just assume it's something really challenging. But if you understand the concept pretty well, you can just take that and just translate it fairly directly into the code. Just be really careful about the null pointer checks. So now that we've gone through the basic operations, why don't you try out these concepts on a new problem? Good luck.
Okay. So how have we done so far? We've got stacks and queues, trees, and not much on sorting and searching. I was going to save that for next week. Heaps. We did heaps. Heaps are cool. The tries are interesting because it's like, well, you'll see. You'll see. It's only 3 minutes, so.
Hi, I'm Gail Lock-McDowell,
Hi, Gail.
author of Cracking the Coding Interview. Today I'm going to talk about tries. This isn't something CS students might have spent that much time on in school, but it's really, really important for interviews.
A trie is a data structure that is actually a type of tree, but it's often used to store characters. And the way that it works is each node might store just a character as its data, but then if we look at the path from the root down to that node, that node is really representing a word or a part of a word. And so what it allows us to do is very quick lookups of a particular kind. So for example, suppose we use this trie to store this very small version of the English language. We could use it to say, hey, are there any words that start with C-A-R? Yes, there are. There's car, that's actually a complete word, but there's also card. So car is also a prefix. So it allows us to do very fast lookups. So let's talk briefly about the implementation of it. So we're going to need a class node, and then rather than having, as we would in binary search tree, a pointer to the left and right node, instead we have some sort of either array of all the children, or more likely some sort of lookup table that maps from a character to that node. So we can immediately say, do you have a child that is an A? Great, give me that immediately. Additionally, we need to understand not just is there do you have an R as a child, an R node as a child, but is that actually a complete word or is it just a prefix? And so in addition to each node having a mapping of from character to node, Each node also has some sort of flag in it called something like is complete word that represents, is that a complete word or not? We see tries in a lot of problems. So if you're in an interview and you get a question that has some sort of word validation to it, so, check if this is, walk through this table and find all the, walk through this Scrabble board and find all the words, or given this list of strings, find all celebrity names. So when you see something that has some sort of word list validation, think about whether or not.
I should mention. I feel like this one's particularly relevant to me also because 2 weeks ago, I interviewed with Zynga on the Words with Friends team, and I played a round of Words with Friends, which is sort of like this online asynchronous Scrabble with a stranger, and I was really marveling at how cool it was that they could find all of the possible words that were available just in one go. And it was, and had I known about tries, I would have just said, oh, it's a try and I know this. But so this was a really interesting and fun lesson for me today, because this is exactly this thing that they must be using in Words with Friends to get all the words quickly. They've probably got a dictionary that has been... Anyways, I thought that was really cool. I think this one's really cool.
List of strings, find all celebrity names. So when you see something that has some sort of word list validation, think about whether or not a try might be useful. There's one optimization that often comes up in try problems. Suppose you had a situation where a user was typing a word, and as soon as the word became clearly it was going to be an invalid word, you want to say underline it. So someone types C, and you say, yes, that is in fact potentially going to be a valid word. And then someone types CA, okay, great, we're looking good. Now they type CAL, yes, okay, there's words that start with CAL. Now they type CALP, oops, no, that's an error. So that's a good case to use a try. Now the way that I've explained try so far, you would do each of these lookups from scratch. You'd say, is there a C? Is there a C? Is a valid prefix? Yes, there is. And then you do, is CA a valid prefix? And you start from scratch over at the root. Now in a lot of cases though, we actually want these calls to kind of build on each other. So one thing we can do with our try is we can keep state in various ways. So when we look up is C a valid prefix, we actually store where we are in the tree. So when the user types the very next character in A, we just look immediately, is A a child rather of C, of that last lookup, rather than starting from scratch. And there's different ways you can actually implement that. One way you can do it is to actually keep state within the try. Another way you could do that is actually return the node back to the caller. So when I say is C a valid prefix, I get not only that's a valid prefix, but I also get information that gives me exact reference to that node. Then, rather than starting from the root and saying is CA a valid prefix, I just ask is A a child of C? And then I ask is L a child of the CA? Et cetera, et cetera. So again, tries are not something that you would spend a lot of time in algorithms classes or in algorithms textbooks, and so they're unfamiliar to some people. But it's a very, very common data structure for a lot of interview questions. So keep an eye out for that construct or that frame of a problem that says something about validation of words, because that's often where we're going to want to use a try. So now that you've understood the basics of a try, why don't you try applying this to a new problem? Good luck.
So there you go. Tries are said to... Oh, my phone is... Oh, that's my brother. I'll have to send him a text later. That was supposed to be on silent. I apologize. Okay. Next up, I found one of the... So, again, I found the interview prep article from DoorDash. The article is available on the GitHub now, so you can track it down. So these guys, they talk about this is the thing about finding your job in tech. They tell you exactly what they're looking for, and they give you the roadmap and they give you the guide on how to be the candidate that they're looking for. So it actually, so if you, Dijkstra's algorithm is, I believe, if I recall, that's about finding the shortest path around a graph. So it would make a lot of sense that a place like DoorDash or Uber or anything that does geospatial analysis, which DoorDash obviously does, because they want to find things that are within a range. You are the user with your cell phone, and they want to know what how far are the drivers from you who would be going out and picking up your content. So it makes a lot of sense that if you're going for an Uber, or if you're going for a DoorDash or a Lyft or something like that, if you're going for any of these guys, you're going to want to study things that have to do with distance. So getting your head around Dijkstra's algorithms, working, they're absolutely going to work a lot with graphs. So, and it tells you about how if you're programming in the, anyways. So that's an article. I'm not going to read the whole thing to you there. They do call out runtime analysis or time complexity. Anyway, and they give you links to things. So, I should reread this to find out how I think I really did. I feel like I didn't pass, but I would be interested to know how it went overall. So, anyways, that's a really useful tool to read up on in your own time. And we are on to, speaking of graphs, here we go. Let's get rolling on graphs.
Hi, I'm Gail Locke McDowell, author of Cracking the Coding Interview. Today we're going to talk about graphs and common operations like breadth first search and depth first search.
Here, I'm also going to pause for long enough to mention that remember that this stuff is loaded into YouTube. All of the links are available to you. You can come back to this. You can do it again. You can you can look at the links directly. So even though we're running at 1.5 speed, you can get this on your own. And this time is really about just making sure that we're sort of putting the time in and just, getting the chance to talk and communicate and keep working on it. So
to go back to the beginning, a graph is basically a collection of nodes where each node might point to other nodes. And these edges can be directed, so like one-way streets, or undirected, so kind of like two-way streets. Now, suppose you want to go walk through this graph, and specifically, suppose you want to do something like figure out, is there a path from one node to another? There are two common ways of doing this, and we'll talk about both of them. The first one is a little bit more simplistic, and it's called depth first search. And it's a typically recursive algorithm. And the way it looks like is saying, okay, we have this initial node that I'm going to call S. Now, you basically are asking a question, hey, S, do you have a path to node T? And S says, I'm not sure. Let me go ask my children. And first S goes to node A, and it says, hey, A, do you have a path to node T? If you do, then hey, I'm done. I can give you my answer. If you don't, then let me go ask B, and then C, and then D. And so the very first person we ask is A. So A gets asked, hey, A, do you have a path to T? I'm not sure. Let me go ask my children. And eventually we might get to a node who says, why, yes, of course I have a path. I am T. And so then we go and say, boop, 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 all the way back up, yes, there's a path. And that's the basics of depth.
I really have to play that again because I do the boop, boop, boop all the time, and that was just really human and relatable to me.
We go and say, boop, 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 all the way back up, yes, there's a path. And that's the basics of depth first search.
Sorry.
It's called depth first search because we go deep into some node before we even ask any of the children. Now, the problem with this is that we might run really, really far away. So imagine, for example, that B actually has a path directly to node T, has an edge directly to node T. A might go to all of its children, all of its children, all of its children, before you even get to B, and T was right there. There could have been a really fast connection. So that's why we might often prefer to use breadth first search instead. Breadth first search says, hey, go level by level out. So first, we ask S, hey, do you have a path to T? And S will say, well, let me check if any of my nodes are T. No, there's no edge right there. So each of those get in line. And then we ask the second level out, and then the third level out, and the next level, next level, next level. And so we go level by level, breadth, we go wider before we go deep. And that's why it's called breadth first search. So I want to talk at a high level about the implementation of each before I dive into some of the details. So depth first search is implemented with a recursive algorithm. It's probably the simpler algorithm to implement. The only little trick is that you have to make sure to use an isVisited flag so that you don't wind up in some sort of infinite loop where there is, a cycle and you keep asking each node if it has, and you start running around in a circle. With breadth first search, the main trick you need to remember is you want to use a queue. So when you look at S and you say, hey, do you have a path to T? You're going to go add all of its children to the queue. And rather than going recursively, you pull out the first element from the queue, check if it has a path, and check if it is this final element, and if not, go add all of its children to it. So you use a queue so that you go through things in the correct order. So that's the high level how it works. Let's turn to the real details of the implementation now. I've gotten a bit of a head start on the implementation, but I'll show you just quickly what I've done. So first, we have this node class here, and it's going to have some sort of ID that represents the node ID. And what I've done is...
Sorry, I paused because I wanted to double check. She said that the depth first is recursive, where breadth first uses a queue. Is that correct? Did I get that in the right order?
Is give ourselves a mapping from node ID to the actual node. And this is mostly going to be used for things like get node and add edge. This way we can actually just go and get immediate access to the node's particular ID. And then I've also given us this has path depth first search method, and it's going to call after this recursive method. So if you remember with depth first search, we need to have a way of flagging nodes to say, hey, I've already visited this, don't retry it. So one thing we could do is we could actually modify the node class to give ourselves an isVisited flag. But that requires then making sure we clear that flag later on. Another way of doing it is giving ourselves a hash set that lists all of the IDs that of the nodes that I've already visited. It's sort of a replacement for a flag. So I'm going to do it this way I don't have to modify and add a whole bunch of flags in and then make sure to clear them later on. So I get the source node, I get the destination node, and then I create this visited hash set, and then I go out and call this recursive method. So now's where the fun begins. So first, if I've already visited this node, if visited.contains this source ID, then return false, because there is no path then. Okay, otherwise, then what I want to do is, so now I want to go and make sure I update this, mark this node as visited. And then I want to say, okay, if I'm at my source, then if I'm at my destination rather, then return true, because yes, there's certainly a path then. Otherwise, go and check all my children and see if any of them have a path, because if there's a path from a child to me, then there's certainly then there's certainly a path from me to my destination. So for each node child in source.adjacent, if there's a path from child to destination, passing in again visited, then return true, and that'll bubble all the way up the stack. If I get down to the very end and I haven't found a path yet, then there is no path from me to my destination. Now let's turn to how breadth first search works. Okay, so breadth first search. So what I need with breadth first search is I need a linked list of sort of what I'll call the next up. So these are I'll call this next to visit. These are the nodes that I need to visit next. And just as before, I need this visited hash set that represents everything I've already visited. And then I want to say next to visit, so the first thing I need to visit is in fact my source. Then as long as there is nothing in this, so while visited, while next to visit dot is empty. So while it's not empty, keep going. All right, so first thing, I need to grab my very first node to visit. So node equals next to visit dot, I'll call this remove. So remove the very first node in that list. If this is my destination, then there's certainly a path. Now I also want to do my visited checking. So if visited.contains of node ID, then actually just continue. Let's go to the next value. Otherwise, visited.add of node.id, so mark it as visited. And then go and actually add my children. So for each node child in node.adjacent, go and add each of those to my next to visit. So next to visit.add of child. All right, and that's all there is to breadth first search. And then of course, if I get down to the very end and I haven't found a path yet, return false.
Right.
So let's walk through this code again and make sure that this makes sense. So hasPathDFS takes in the source and destination IDs, and then I get those nodes, and then I create this hash set. That should be a hash set, not a hash map. And then goes and actually does this recursive method. So the recursive method has this visited thing, so we use the visited hash set instead of marking the actual nodes with a flag. So the visited, checks if it contains the source ID. If it does contain that, if I've already visited this, return false, because there's no path then. Otherwise, go and add this visited, mark this node as visited, check my source and my destination, so if I'm already there, return true. Otherwise, go and search all of my children. And then if I haven't found a path, go return false. So with BFS, we are taking in a source and a destination. So here I've used nodes. I'll switch this actually to be symmetric. and use IDs again. And so I'll make that public and this private now. Okay, so I take in the source and destination IDs, and then I go and call this recursive method. So my recursive method, or sorry, this other just helper method. So this takes in the source and destination. I create this list of the next nodes I have to visit, and this visited hash set. This should be hash set again. And this marks all the nodes that I've already visited. So I say, okay, next one to visit is my source. Then as long as there's something left to visit, pull out the next node to visit, check if I'm where I should be. If so, return true. Otherwise, check and update my visited, who I visited. And then go and queue up my children at the very end of the queue to be visited next. And this will ensure that my children are not visited immediately, but are visited once sort of everything scheduled has already been visited. So to ensure it'll visit level by level by level. And then if I get down to the very end and I haven't found a destination after all of this, then just return false. So that's how breadth first search operates. In many cases, when we want to find if there's actually a path, breadth first search is often the better approach, because otherwise we could wind up searching really, really far away when there's actually a very short connection. And it's certainly better when we want to find the shortest path. So now that you've seen breadth first and depth first search, why don't you try these out on a new problem? Good luck.
Right. And so good time to remember, especially with this graph stuff, with this depth first stuff, and in the context of getting hired in Toronto, we have two major players. We've got DoorDash and we've got Uber, who are both in town. Uber is planning on hiring 50 engineers before the end of the year. I don't know what they're at now, but there are likely to be, let's say 20. There are likely to be like 25 positions still open at least. I don't know. And they'll probably take as many people as they can get. It's just so, graphs are going to be really important if you're looking for a job in Toronto. Also, DoorDash is getting started on setting up their offices here. And so for DoorDash, we're talking about, they're going to scale up an entire development office. They're probably chasing after Uber. They say if Uber's launching something in Toronto, we want to be able to steal Uber's people. And so, anyways, and skip the dishes. Yeah, skip the dishes as well, because they have to talk about the distance to the drivers. And so all of the companies that are sitting in that space are going to be really hot on graphs. They're going to be really hot on the traveling salesman problem. And so if you're looking to get hired in Toronto, that's a really strong area to focus on. And so watching an 11-minute video on 1.5 speed, if you're targeting any of those high-end employers, is probably not enough. Go into your LEET code, go into your hacker rank. We'll bring, hacker rank has questions that are organized by the type of data structure, I believe. So if I go to data structures, right? So here, I can actually say, give me what? I was talking so much smack. I was expecting I would be able to see a graph in this list, and I don't. That's embarrassing. Advanced? Are graphs just counted as advanced? Okay. Trees. Binary search tree. Anyways, I'm just saying that you can actually get questions. I should do Heaps myself, but here you go. Advanced. Are any of these? I can't believe it. I can't believe I told you that you would be able to find graph questions, and I wasn't able to find any. Anyways, that's not important, but maybe algorithms, maybe they'll have debugging, NP, game theory, recursion, bit, graph theory. Here you go. So many questions on graph theory. In all fairness, I'm comfortable saying that the DoorDash one was not a graph question, but you know, if I did get through, I don't think I'll get through, but if I did get through, it would be a pretty strong bet that they might expect a graph question because remember when we were talking about how the interviews go in big tech, they do a phone screen with a recruiter to see that you're, not too bad. You do a brief technical, you do a 15-minute technical with the hiring manager. Then you do a coding algorithm problem, which is a 1 hour interview where you have 15 minutes of just tell me who you are, and then it's 45 minutes of solving an algorithm problem of the type that you would see on a hacker rank. And then typically for the final interview, it's between 2 hours and 4 hours, in some cases even 5 to 8 hours, right? Like the final interview can go for a whole day long, where you have 5 of these sessions where you are solving and solving and solving. And it would be fair to assume that if you were making it through to the final round on a DoorDash or an Uber or a Skip the Dishes or a Lyft, that you would expect probably to see at least one Dijkstra's or at least one graphing question, because searching for paths and searching for distance and searching for routes to find where you're going are so critical to their business. Anyways, so we've taken care of that stuff. We can close those. How are we doing for time? Actually, we're taking a little longer than I thought. I am a very wordy person, I guess. So I'd like to do this one and this one. And I think the Netflix one was interesting.
Grammarly helps you work more efficiently, which makes accomplishing your work goals easier.
Netflix had been traditionally hiring only super talented people, and while this still applies today, their hiring operations have since expanded internationally. And as more and more people starting to apply for jobs at Netflix, there's also an increasing amount of information available about the application process, and specifically about the questions that they're asking during jobs interviews. And in fact, there are around 1,000 such questions reported online, which I indexed into a list with the 7 most asked questions during any interview at Netflix. On number 7, we have, tell me about the time when you did not agree with your manager. And I believe this is a quite a common question for any sizable corporation, and it's basically looking to see how a job candidate would perform within a team context.
Grammarly
And whether there are any...
Sorry about that. I'm just trying to see if his description has... I'm so sorry. I screwed that up. We'll skip back. I was trying to see if he said he compiled a list of the questions, and I was trying to see if he...
Once. Instantly accept.
Oh, that's devastating. Let me skip back.
With the 7 most asked questions during any interview at Netflix. On number 7, we have, tell me about the time when you did not agree with your manager. And I believe this is a quite a common question for any sizable corporation, and it's basically looking to see how a job candidate would perform within a team context, and whether there are any subordination issues there. On number 6, we have...
Right, so again, we're moving from... It would be nice if we had some time to stop and think about all of that algorithm stuff. Realistically, you're going to want to go through the algorithm stuff again, make sure you're still doing your hacker rank, but also taking some time to focus on, remember the behavioral, start thinking about ways that you would answer these questions if they were asked of you. So I'm just going to...
Tell me about something that you worked on that you're really proud of. And the main reason the interviewer is asking you such questions is because they want to see on whether you can make a difference as compared to other candidates. And I actually call these questions as gifts, simply because they allow you to focus on your strengths. Now, what are your strengths? Well, that varies by positions, but as a general idea, I would always use my successful projects within a team context if possible. Number 5, how do you stay organized? How do you handle competing tasks or projects? Now, this question as well touches upon one's management skills and your ability to prioritize competing items. And of course, here you want to show that you are, well, being a great listener and a team player, you actually go above and beyond to get the job done. And of course, think of a situation that would emphasize on this core competency. Number 4, what has your biggest challenge been while at work? So the main reason why anyone would ask such a question is because they want your ability to handle challenging situations. So whatever situation you choose here, make sure it's probably a recent one that highlights a core competency, something that's relevant with the role that you're applying for. And last but not least, you always want to emphasize on you being a great team player and willing to listen to other parties if this was within a team context. Number 3, describe a time when you received extremely difficult feedback and how you handled it. Now, more often than not, these types of feedback comes from a higher up, and what you want to emphasize here is your ability to listen and to always act in a certain diplomatic way, so that you reach the best possible compromise here. And of course, you shouldn't avoid showing up a bit of drama here to make the situation really feel like genuine, but at the end of the day, you should really ensure that you're not putting the blame on anyone, and if you can, try to highlight also some positive aspects and your main learnings from such an encounter. And the second most asked question at Netflix is, tell me about your work experience, and more interestingly, why do you believe that you can make the difference at Netflix? And this question is a synonym to why Netflix. And probably the best template that I know to answer why Netflix would be, I want to work at Netflix for the following 3 reasons. And what you want to be careful here is to emphasize both that what's in for Netflix as well as what's in for yourself if you get the opportunity to work there. And the number 1 most asked question during any Netflix interview is, what do you think about our culture memo? Now, I'm sure that by now you've already heard about this, and I've also made multiple videos on this topic, but I cannot emphasize enough how important it is for you to really go through that memo and understand some key takeaways on what's different at Netflix as compared to other even high-performing companies, because there's really something special going on there. Now, this being said, as always, I hope you found this information useful, and thank you very much for watching.
Okay. Yeah, the culture memo from Netflix was pretty interesting. I thought it was pretty good. It is worth reading. Anyways, rather than going through all 19 minutes of this one, these are some of the common things. Overpraising the company. So if you walk into Netflix, you walk into Amazon, you walk into Google, and every third word out of your mouth is, oh my God, I love Netflix so much. You're wasting the interviewer's time. And they're going to say, right, but I'm trying to find out if you're a good candidate. Don't, you can, obviously you want to be a little bit excited, but you don't want to go crazy. I think that if you are coming to this on a weekly basis, you are not going to have this problem, but one of the things that they say is many people do not go into their interviews having studied their algorithms, have not studied the behavioral side of things. And so it's really important, if you're going in, make sure you prepare. This is one that I have to work on probably, is keep your answers short. Keep them to about 1.5 minutes each, because they have a lot of things they want to ask you. And so try and be concise in your communication. Don't be overconfident. Don't go in thinking that make sure that you have some humility in terms of things. Nobody likes a jerk, so worry about that. Time management. Honestly, I should have taken better notes when I watched the video the first time, because I don't know what this was about. I can't remember. Admit when you don't know an answer. So if you are in a place where you don't know, the interview is more often than not there to help you get through and wants you to be a good candidate. They want you to be successful. So if there's something that you don't know or don't know how to solve, don't bullshit. Just say, I don't know, and try and work on that. So the next one is not a don't, but it is a do. Do make sure that you get feedback coming out of the interview, regardless of whether you're successful or not. Some companies will not give you that feedback. They will not, and that's for legal reasons. But if they come to you and they say, I'm sorry, we've gone another way. I'm sorry, we've decided, if they come to you with a rejection, the first thing you should ask before you go down to the building and light the building on fire and burn it to the ground. Don't really do that. That's a joke. But the first thing you should ask before you take any time to get upset or feel the emotions that come with being rejected for a job is, thank you. Can I have detailed feedback regarding areas of improvement? Or can I have detailed feedback on the decision that was made? At this point, if we imagine that you've gone through to the full day interview, or if you've gone through to, even if you've gone through the 2 or 3 hour interview, if you do not get feedback, you're walking away empty-handed, and you will have spent those hours for only the minimal value. And I think I told this story last week. I got detailed feedback from my Zynga interview where, maybe I didn't tell this. Anyways, I can tell it again. I'll tell it quicker this time. So I went to a Zynga interview. I wrote the code, and I wrote it in a brute force fashion. So what I wound up having was an n-squared algorithm rather than the optimal solution. I did tell this story. The optimal solution was an O of n solution. And my feedback was for the level of employee that I was expecting to come on board as, for the amount of work experience I had in the world, the hiring manager would have expected an O of n algorithm the first time, not just solve it with an n-squared, say, here, I've done it, and then say, and if I was doing this in if I was trying to do this in linear time, this is how I would do it. More important for that, at the stage that I was at, and probably, hopefully, the stage you're going to be at, solve it optimally the first time. And I wouldn't know that was the reason I was rejected unless I had received feedback, unless they had told me that was the reason that I got rejected. So get your feedback. Get your feedback. Get your feedback. Anyways, the next one is, and so that feedback was wonderful. It has helped with every step along the way because it just doubles down. It really hammers home, do things the optimal way. Next one, network. So you've, in theory, met with 2, 3, 4, maybe more people at a company that you want to work with. They have friends. Sometimes maybe they're hiring again in future, and just talk to them, be nice, try and maybe make a permanent connection. Finally, do not go in bad-mouthing your old place. Do not go in talking about how tough your life is. You're not there for a therapy session. So as Dan Kreuter says, he says, be positive and optimistic, and or if you don't have anything nice to say, don't say it. Focus on the positive, focus on what you want to do at the place you're going. So these are some of the things to think about in terms of the behavioral and human side of this. And practice, tell me about yourself. I don't know. You can watch this on your own. We're running out of time, and I had actually promised that we would be done by 8:30. So let's make sure. Oh, what's this? Be nice to the recruit. Yes, absolutely. Be nice to recruiters or hiring managers, as they often leave companies and might ask you to interview at their new company. That's right. One of the things that I've made a conscious effort towards is actually even to be nicer, to be actually not nicer, to be nice, to be respectful and polite, even to the recruiters who show up on LinkedIn and very clearly haven't read your profile and they, hey Alex, I hear that it's like anyways, there are recruiters that we all know the difference. There are ones that have read your profile and ones that you kind of can tell that have not even checked on you. Be nice to those ones as well. Just be nice to everyone. It's a good rule, but even those ones, again, I'll say it again, even those ones can at least tell you the salary budget of the role that they're hiring for. And so what you get is you say, hi, thanks for reaching out. How much does this role pay? And they'll say, I'd love to get you on the phone. I'd love to get you on the phone for 5 to 10 minutes and we can talk about it. And you say, I'm very busy. I want to know. Yes, I reached out for Java Dev, JavaScript please position as well. Right. So it's like they're asking you to do Java and you're looking for JavaScript and you say, do you not know? Can you not tell? Can you not tell that my iOS experience was 15 years ago? Anyway, or 10 years. Well, that's impossible. But anyways, point being, be nice to everyone. Even if you're talking to those ones who clearly don't know who you are, you can still find out the salary budget of the role that you're that they're trying to get you for. And that will tell you, how does my salary compare to this one that they're talking about, right? And so if you get a whole lot of those recruiters reaching out and each one said, if you're on 100,000 a year and you get 5 recruiters in a row that say, oh, this salary budget is 150,000. You say, well, this isn't lining up, right? And so you can talk to your company, but more accurately, it's probably better to start looking outside. And I will find some resources on that tells you the game theory around why it's better to look externally to get your big raise. It's very hard to internally get a big raise, but if you jump to another place, it's much easier to get that jump that you're looking for. If you've ever, actually, I have a metaphor there. If you've ever heard the restaurant marketing colloquial wisdom is it costs 4 times as much money in advertising to get somebody to come into your restaurant for the first time than it costs to bring somebody back a second time, right? And that kind of makes sense. So if it costs you $25 in advertising to get somebody in the first time, it only costs you $5 to bring them back in advertising. Usually even less if the food is good enough. So the inverse seems to be true for keeping employees around, because from your perspective, anyways, it's maybe a bad metaphor, but I'm just saying that if you are looking for a large raise, the best way to get it tends to be to go to another company. And there is tons and tons of writing out on the internet about that. And I will track it down and I will find it for next week's lesson. We can even ask Amy about that. She will tell us as well, I bet you. I want to make sure that we have a more robust homework assignment Rajat, are you doing your algos? Pebs, are you doing your algos? Doing your practice. Solve 4 easy and 1 medium. We're gonna double that. Because the easy, I did a few easies as well last week in mediums, so maybe I should prove. So we're gonna say, was 4 easy and 1 medium a reasonable number or hard? Let's say 6 and 2, right? Is that fair? That seems good. Do 6 and 2. There we go. Doing hacker rank and studying C++ again. Nice. Ooh, this is exciting. Speaking of studying things, I have been getting, I don't know, did I show you this last week? Clean architecture. We have a week on system design coming up. I think I showed you this one, and practicing. And I have been buying textbooks, design patterns. This one is the Gang of 4. Clean architecture is really good so far. And what else did I pick up? I got clean architecture and clean code. Again, these are, so one of the things that I'm planning on doing, that I'm in process of doing right now, is as I read through clean architecture, I'm taking notes, writing them down, and I plan to record a summary of each of the, I can just be direct to camera now. You can still hear me now. So I can just do a summary of the chapters. I'm going to lay them out. And so in theory, that would be like a crib notes version of clean architecture for you to study from. So that one I think would be really useful and fun. And what else am I working on? Anyways, I'm working on stuff. Oh, and in celebration of my excitement about the new job, I ordered an amazing camera. So I got a really cool camera and lens, and it's going to be a higher quality. Hopefully, I would hate to spend that much money. It's like a mirrorless DSLR, and so it'll be like super high quality, camera picture. I've got, in theory, if he comes through, I've got a guest lined up for the interview channel where I'm doing, I have an interview scheduled, and fingers crossed he can still make it, but it's an interview with a fellow that is a senior engineering manager with Netflix. And I'm going to ask him about his career and how he got, how he started in programming, how he got to Netflix, what it's like working at Netflix, what the course of his career is on each of those steps along the way. And I'm super excited about that because I've been following this guy on Twitter for a while. And he just seems really smart and cool and nice, and like he's going to tell us some stuff about what's on the inside. That's not part of the course. That's on the... have I pasted this to you yet? I do have the YouTube channel. Maybe I go back to my... I'll go back to this one. I like this fancy layout. So I did this decal here, and I did these borders and this logo. The background, the vaporwave background, was a stock photo, but that's a bit of art. This is actually, so here's the other thing. Thanks to everybody who did subscribe, because I now have a YouTube channel name, LGTM Ship It. Bam! It goes to my channel. How exciting is that? So this is, if you don't know, there is an interview channel where I talk with programmers that I have worked with. about their careers in programming, and it's how they got their first job. It's how they moved from job to job. Jordan's blew me away. He was so smart and clever, and he spends so much time on professional development that he really inspired me to be better. And I have an interview in the can that I'm going to be working on editing after this. What time is it? 59. So we're going to run out. Anyways, so Jordan is so smart, so inspirational. He's gone from in the time that I have known him, he has gone from a sort of brand new junior web developer doing HTML markup and emails to he is running a machine learning mega computer on Kubernetes. He's got, I think, 2,000 CPU cores on 70 machines, including 8 high-end NVIDIA graphics cards. And now I feel bad because I feel like I'm underselling the rest of the people that I've talked to, but like each one of these stories is the story of a programmer who has, a really interesting life and career. I'm really excited about my interview with the senior manager at Netflix, senior engineering manager at Netflix, and I have 2 interviews this week, and both of them should be really fun. Good friends of mine. So there. Oh, I said this is what I actually came along to do. I was going to paste that in there for you so that you could have it. And I think. Oh, what's the last thing we should do? Coding interview roadmap. The interview roadmap. So we have just finished from week 0. We have finished week 3, which means I think I looked ahead because we have practiced simple data structures. This one again is just keep doing the algos, keep doing the algorithms, keep doing the data structures. I'm not sure quite how to handle that yet, so I think definitely we have the interview with Amy. She's going to come along and tell us a bunch of insider information about getting hired, and the process in general. That's going to be really interesting, I hope and think. Then maybe we break down a couple of these questions and go through algorithm type solutions. And that's the story of this. Oh, and I was going to say we'll put sorting and searching either next week or the week after, depending on how long Amy goes. I've only booked her for a half hour, but if she has fun and we have fun and it feels like there's a lot of interest, maybe we get a little bit more time out of her. That's not guaranteed because I only asked for a half hour, and she is a very busy person, I am sure, as a high-achieving recruiter in tech at FAANG companies, as well as her sort of self-run. Thank you, Rajat. And with that, I will be ending the stream, and we will talk to you hopefully next week. And I hope that you enjoyed it. I hope you all enjoyed it. You and Pebs, the 2 people who are here. But we actually get some viewers on YouTube as well. So I know that there are people who watch it without logging in because they don't want their name out in the public. They don't want their boss to say, what are you doing watching a how to get a job show? Which makes some sense, so there we go. Okay, ending the stream. Thank you so much for coming along. I've once again had a really great time, and we will talk to you soon.